SwayamPrabha. Digital India. Educated India.
Okay, last class we were talking about bypass transition, that is triggered by a single vortex convecting in the free stream. An experiment was conducted whose setup is shown in the schematic here. This is the side view of the plate and this is the vortex which is at a height h. This vortex is created by rotating a cylinder. The rotation rate is given by capital omega. C is the speed, constant speed of convection, and there is in addition the free stream speed u infinity. So, both are in the same direction. So, you have a basically relative velocity between the two. And if you look at the top view of the experiment, then this is your rotating cylinder and this is the leading edge of the plate. There are 6 die ports which eject die in the inside the shear layer, and we did this visualization experiment that was reported in this paper in Experiments in Fluid volume 37, and the results were quite interesting, namely that it showed us certain features of the flow, and these were the various cases that we studied. First 2 cases corresponded to where the cylinder was rotating in a counterclockwise manner at a rate of 5 rotations per second. The vortex was at a height of 27 delta star above the plate, and in the first case the speed of convection of the vortex was 0.386 with respect to the free stream. In the second case it was just the double of it. Okay. The third case was created just to show the importance of controlled nature of such receptivity experiment. In this case the cylinder was just simply translated, but there was no rotation, and of course, then this last parameter which basically gives you a ratio of the surface speed divided by the relative speed of the free stream with respect to the cylinder. So, in that case surface speed is 0. So, that is what you are seeing. So, this is a case of pure translating cylinder. Case 4 and 5 corresponded to clockwise rotation of cylinder, the same rotation rate. The speeds were kept lower because we will see that this is not very receptive while this is so. So, in this case also when the cylinder was rotated in the opposite direction. So, you created a captive vortex of opposite sign, and while the other parameters remain the same, we wanted to see what happens of different vortex effect. The last 3 cases were as same as the first case because the convection speed is kept the same, the rotation rate of the cylinder is kept the same, it is only the distance that were varied, and there were 3 such cases. In one case it was brought closer, the other case it was brought somewhere closer to the cylinder, and this was when it was relegated farther into the free stream. So, we did see the cases. The case 1 that we shown was this. What we saw was the same plan view picture that we saw here. This is the way the picture were taken. So, this is in this sequence. So, the cylinder is moving like this, and these are the die streaks, and this is the second frame, the third and fourth. So, it has gone on that way, and as you can see, when the cylinder was somewhere beyond the die streak, you do not see appreciable disturbances. However, that sooner or later starts picking up, and once that primary instability sets in, that in turn leads to secondary and tertiary instabilities that is manifested here by rapid diffusion, mixing, and even the chaotic nature of the flow, that is what you see in subsequent frames. And the good news about this is when the cylinder is crossed over, again you get back to your undisturbed flow. This is what we have talked about in the last class, that what you need to do is a kind of a control experiment, and the control experiment will be such that you would have control over each and every parameter of it, and when you remove those parameters one by one, you should be able to get the undisturbed flow by itself. Okay. When and how this can happen? This can happen if by nature the flow is such that in the absence of disturbance, the flow is essentially laminar. Okay. So, this is what we did talk about. Now, let us talk about the case which we call as a case 2. The speed of convection of the captive vortex has been doubled here, and upfront I am telling you that there are no violent breakdown of the flow. However, what happens is this is the scenario that you see in the field of view here. Since the rotation rate is same, height is same, it is only the speed that is varied, and you see this is the way the sequence has gone on. So, the captive vortex keeps moving, but the underlying shear layer does not react to it. So, it is kind of pretty much obvious to say that if you want to see study the receptivity of the same boundary layer with a vortex of the same strength kept at the same height, the speed is a distinctly important parameter. How this thing comes about, we will explain as we go along. This is what we are talking about. The last point, please note the range of translational speed that we investigated. We found that slower the translation speed of the vortex, greater is the adverse effect of the boundary layer stability when other parameters are kept the same. So, this is a generic observation that we can draw by looking at these two cases. Let us try to explain what is happening. You see, we have kept a vortex, it is a captive vortex which is very much outside the shear layer. So, it does induce a kind of a disturbance stream function. The disturbance stream function has two parts. One is due to the vortex itself, another is due to the cylinder. The cylinder is represented by a doublet in a uniform flow. And what is the uniform flow here now? U infinity minus c, because both of them are going in the same direction. So, the relative speed is U infinity minus c, and this 2 y corresponds to the uniform flow path, and these corresponds to a doublet and its reflection, because it is going in front of a flat surface. So, you get a reflection the same height. In one case it is plus h, in another case it is minus h. So, this is due to the actual vortex, the doublet, and this is its reflection. Okay. The same way you have a vortex captive with the cylinder that creates this circulatory effect, and you can see again the numerator and denominator respectively gives you the image and the original. Okay. And you note that we have indicated the x coordinate by x bar, where x bar is basically the location where we are studying with respect to the vortex location. So, x minus x v is your x bar, where x v itself is given by x naught minus c t, because it is moving at a constant speed c. Okay. So, what you are seeing is basically this two effect. This I will call it as a circulatory effect or circulation effect, and this is what I will call it as a displacement effect. Right. Now, you have this expression for psi. So, there is every possibility that you could work this quantities out yourself. Okay. As I told you, the expression takes account of the image system, and the dynamical system is destabilized inside the shear layer in a receptivity scenario, right, because we are creating a definitive disturbance and we are studying the response. I told you there are two effects, the displacement effect, and if you look at the expression, it depends on C, d diameter of the cylinder, and h the distance. Well, pretty much obvious. C is there because we are talking about the relative speed u infinity minus c. That is how C appears here. Then d is of course the size of the cylinder determines the dipole strength, right, the doublet strength. So, that is the displacement effect. Bigger the diameter, more the displacement effect you would have. And h is coming into the picture because of the way that the doublet is above the plate at this height. So, you have another image also at minus h. So, that is how in the displacement effect h comes into the picture. Okay, the circulatory effect is basically nothing but your Biot-Savart interaction. That is very easy. That depends upon, from the expression we can see C, H and gamma. Now, you may ask me a question that we did not see the expression for C here. We did not see the value of C appearing in the circulatory effect. How does it affect? Well, it's a subtle thing, because we are creating a relative speed, and that relative speed, if you recall, would create, as the cylinder is rotating, that creates the circulation. So, gamma itself that we have here is a function of C. That is why it is, and dependence on h is pretty much obvious. And of course, you can also say that C comes in through the definition of x bar, because that is what you have there. Now, what happens is we can look at this expression. So, this is the disturbance stream function. So, if I really now consider a control volume over the flat plate, this is the disturbance that is created by the convecting vortex, that we can put it on the boundary of this control volume. So, what we could do is we could really estimate, depending on the coordinates x and y, what is it that we are getting. In this set of figure, we have shown the following quantities: the disturbance stream function itself as a function of x, that is plotted, and you have two paths. One path corresponds to the displacement effect, this horizontal effect quantity, and we have put in the vortex somewhere here along this vertical dotted line. Okay. So, what happens is, of course, the disturbance is maximum in the vicinity of the cylinder and it falls off, and this is due to the circulation effect, the gamma part. So, if I parameterize the value of gamma and I can work out an expression, this is how that circulatory effect would be. However, displacement effect remains flat. Okay. It remains the same for all x's. That is what you are seeing. In the second frame, what you are seeing basically a plot of the pressure gradient induced by this disturbance vortex as a function of x. And once again, what you notice is that around the mean position of the cylinder, you have on this side adverse effect, adverse pressure gradient, on this side you have a favorable pressure gradient. This is the case that is corresponding to case 1 and 2, where we are talking about a counterclockwise vortex. So, what you notice that the moment you have a counterclockwise rotating vortex there, ahead of it you see adverse pressure gradient, behind it you see a favorable pressure gradient. Now, this is something you can convince yourself, like what we seen before here. If I come back to case 1, what I notice is the flow is getting destabilized ahead of it, and that is the expression that we worked it out there. And you can also see a very interesting thing, that ahead of the cylinder the die streak meanders, but behind it it stabilizes and it becomes again smooth and nice, and that you can see that when it is completely removed, you get back your undisturbed flow. So, it is not only it is undisturbed flow, but because of the favorable pressure gradient it actually stabilizes the flow, and that is precisely the expression that we noted there from that pressure gradient versus x plot. Okay. Now, we have shown two cases of the pressure gradient for different values of C. One of the value is 0.1545, okay, very low speed, another is 0.77. Okay. We had done this visualization cases. I did not show you 0.15, but 0.15 case had a much larger receptivity. That is why we commented that lower the speed, lesser will be the effect, more will be the effect, and higher the speed, when the relative speed comes to almost 0, then you would not see any effect at all. But this figure seems to contradict that. Now, why is that so? Why is that so? See, this is what we are talking about. That is the last point that we are talking about, that the imposed pressure gradient as a function of x for the two indicated values of C was shown in that frame. That what we notice from that figure, that the imposed pressure gradient does not vary appreciably with C. An adverse pressure gradient for both the cases occur at the same downstream location. However, case 2 showed no receptivity, case 1 did show. We have talked about this, that we have a stabilizing favorable pressure gradient upstream of the pre-stream vortex. The boundary is given by the vertical line, and the adverse pressure gradient is mostly determined by the circulation effect. Okay. And the induced adverse pressure gradient that can destabilize remains constant for same gamma when C is varied. Now, this is what we observe. Now, we pose the question that it seems counterintuitive that we have same adverse pressure gradient, but case 1 shows receptivity, case 2 does not. Why? That you need to understand if you look at the time variation of the induced pressure gradient at a fixed location. What we had done, we have talked about looked at around a fixed location x equal to 5, and the vortex is moved from x naught equal to 1 at t equal to 0 to t equal to 30. In this motion from 0 to 30, what happens to the pressure gradient as a function of time at x equal to 5? That is what is plotted in the third frame. Now, that is what is plotted in the third frame here. So, this is pressure gradient versus non-dimensional time. What you notice is the following, that if your vortex is not moving, then you are going to get the case of C equal to 0, and in that case, of course, at that fixed location the pressure gradient remains the same. And what happens is that is an adverse position. So, you have put in the vortex at x naught equal to 1, and at x equal to 5 you are looking at it. So, what does it do? It basically creates a adverse pressure gradient ahead of it, and that remains invariant with time. Now, you look at this case, this top figure corresponds to the case of C equal to 0.1545, okay, whereas this curve corresponds to C equal to 0.77. Now, what you notice that adverse pressure gradient magnitude, maximum magnitude is more for 0.77 case, but it just becomes favorable after a short time. Whereas, for the case of 0 to low values, the adverse pressure gradient remains adverse over a long time. For 0.15 case, you can see the the flow is experiencing adverse pressure gradient over such a long period, and C equal to 0, it is even more interesting thing that you have the same level of adverse pressure gradient all the time. So, what happens is you can see the role. I mean it's not a static system that we are studying. We are looking at a dynamical system. So, the time history is important. So, what happens is 0.77 case, although may produce at a fixed time the same amount of adverse pressure gradient, but that maybe even little more, slightly more. As you can see, this curve goes slightly above 0.77 compared to 0.15. That is true here, but after some time it falls off. So, it does not show that much of receptivity. So, it is not only important that you must have an adverse pressure gradient, but it should also act over appreciable period of time. That is an important issue to look at. Okay. And the last quantity is that Faulkner-Scan parameter that we have defined as m equal to x by u e d u e dx. This is the non-dimensional pressure gradient parameter that we have plotted there, and what we show the top curve corresponds to t equal to 0. So, at the initial instant what is the variation of m with respect to x. This case is shown for a low value of c. This value of c is 0.1545. So, at t equal to 0, m variation is like this. What is this dotted line? This dotted line corresponds to the case where you have a steady separation, steady flow separation, right. So, we know that it does so. So, what happens is even at initial time instant, then we have a range of x where you have adverse pressure gradient that is more adverse than what you get for steady separation. So, in a dynamical sense, you do create much larger adverse pressure gradient. And if you keep now looking at it, this snapshot as a function of x that is shown here for t equal to 0, at a later time you can see it keeps becoming more adverse, and it becomes adverse over a longer stretch, and even the adversity increases in quantum. You can see this is the case where actually you get the maximum adverse pressure gradient at this location. So, this is roughly around t equal to 23, this time is around 23, maximum adverse pressure gradient is here, but you see at this location shown by this dotted line where you see that first primary bubble, that unsteady separation starts from that point. So, you can see that it is a very complex case. So, although it may appear that everything is in a static case, you have a steady boundary layer and you have a vortex that is going at a constant speed, but you can see so much of unsteadiness involved that is shown in this last two picture. So, basically I would assign you a homework which I would expect you to hand it in by next Monday, where you would be doing a much more detailed study of all this. So, I would I will send you an email, you can follow it up what has to be done. So, we have talked about all this, we have talked about, we have seen all this before. So, what we are now going to do is we are going to talk about the case where when we compute the Navier-Stokes equation at t equal to 23 at this location we saw the unsteady bubble start forming, unsteady separation start forming. This is what we call as the primary instability, and in the following what we are going to do is we are going to show some bit of computational result of it. Okay. I explained to you those horizontal dotted line is drawn at this value of m, for which the similarity flow suffers steady separation, and well, we are looking at truly unsteady flow which can sustain much higher values of m and still do not show separation. So, this is something you must understand, that Prandtl's criteria of steady flow separation is just a very empirical observation. It was just stated that where tau equal to 0 would lead to separation, but we see here in such cases we have much more adverse pressure gradient, and still we do not see. Now, let us look at the case, uncontrolled case. That is what we are talking about. This cylinder is just simply dragged along at this speed 0.386 of u infinity, height kept the same, but it is not rotating. When it does not rotate, you have seen the expression for psi, the circulatory part is 0. So, whatever you are getting is basically a displacement effect, and if you drag it along like this in sequence, then you see nothing really happens. So, this was what we talked about, also the experimental result of Tokumaru and Dimotakis, the JFM paper, as well as Diaz et al. That physics of fluids paper, which had established the case that if you rotate it at a high rate, it does not, but even in this case we do not rotate it, there might be vortex shading, but because of this large distance of separation between the vortex that is in the free stream and down below, what you are seeing essentially is only the displacement effect. That is not good enough to create the instability. That is why this whole phenomena we have called it as vortex induced instability, right. So, as you can see, this is what we are calling as vortex induced instability. Why did we add the word subcritical? That should be pretty much obvious to you, because in the absence of any disturbance, flow remains quiescent. It is only when I disturb the flow I see the response. This can only happen if it is subcritical. If it was supercritical, then of course I would not see that. The flow itself has a tendency to become unstable. Okay. So, that is what we are saying, that in this case of non-rotating translating cylinder, we do not see any violent instability for two reasons. Firstly, the imposed disturbance field as given by that equation has no captive vortex, gamma equal to 0, because the cylinder does not rotate while translating. Secondly, even if there are shed vortices, they will be very weak, and the corresponding Bénard-Karman vortex is seen to affect the flow rather very weakly in far downstream location. Why it does affect farther downstream location? That is where your boundary layer is growing, your Re delta star is growing, the transfer function is becoming more and more receptive to smaller disturbances, and that is why you may see some weak effects there. That is what we are saying, far downstream of the translating cylinder, only at some earlier times. So, this could be essentially due to the transient. Now, we show a case where the cylinder now rotates in the opposite direction. The rotation rate is kept the same, translational speed is reduced. We have seen now that if we make it dwell, make it go slower, then the adverse pressure gradient will be sustained over a longer time duration. So, if the flow is receptive, it will be doing that. Now, come to think of it, what the flow is doing. If this cylinder is going like this, and consider this is a boundary layer in this direction. Now, if I rotate it like this in a counterclockwise manner, then what does it do? What is the induced effect? It will try to scour out the boundary layer. It tries to pull it up, and that is what we are seeing. I mentioned it very clearly in the last class also, that when you look at the die, that you see there are two things. One is one layer that remains parallel, very much embedded, and the other one has been lifted up on its own plane. On its own plane. So, it is basically a two-dimensional phenomena, and this is due to this induced effect. So, that is why we called it as a vortex induced instability, and because it is very much dependent on the large excitation, this must be a subcritical case. Okay. Well, these are some of the other references where experiments were conducted by Jim Kendall at JPL, and he talked about boundary layer receptivity to free stream turbulence in this paper. But you see, this is what we have highlighted in the last class also. You can do an experiment, but if you cannot reproduce it time and again, then it becomes very, very difficult. Even though you are working in the same tunnel, it is very, very unlikely that two realizations would give you the same thing. That is because you are not doing a subcritical study. Here we have done a subcritical study to understand what the mechanism is, and we can reproduce it time and again, So, this is something that we must understand. So, now let us take a look at the case 5, where the vortex is in a clockwise direction, and if the vortex in the clockwise direction, the vortex is moving like this, like what we have shown here 1, 2, 3, 4, 5, 6, 7 in this sequence, then you can see what is happening. It is going on all right, the dies are smooth and parallel, nothing much happens in front. But do you see there is a bit of a swelling little in the behind the cylinder growing up? Now you can see distinct bulge here, some kind of a mixing, spano is mixing, and so on and so forth. So, what happens is, in this case, the effect is occurring upstream of the vortex, and this is once again the same logic that we talked about. Think of the boundary layer like this, and let us say it is going in the clockwise direction like this. If it does like this, then in the front it tries to reduce the thickness of the boundary layer, it imposes a downward velocity, whereas upstream behind it, it has the other effect, it tries to scour it out. So, this is the kind of explanation that you can immediately see. Well, you can see then that if you are going to experience some kind of a vortex induced instability, then you can take appropriate action. And what you notice is that clockwise case was more violent as compared to anticlockwise case was more violent compared to the clockwise case. In the anticlockwise case, what happened? The disturbances were ahead of the vortex and it was much more severe. Whereas, for the clockwise case, it happened behind the vortex and it is of a much lower intensity. This is what I told you about. Not much of qualitative study has been done, but one can correlate what we have just now observed to what people experience in a flight, what is called as due to convective clouds going in the vicinity of the aircraft. You must have heard during the flight pilot telling you to fasten your belt. It is that, it is basically a vortex induced instability. This convective cloud have associated vortices in them, and if the aircraft comes very close to it, it does get affected. However, if you are a pilot, you know what to do when you are approaching a vortex. How do they detect vortex in an aircraft? Any idea? Well, they use some kind of a Doppler radar, and from the humidity content they try to detect. I do not know whether it is feasible for the Doppler radar to basically tell you about the circulation, but if it does, let us say, then the pilot can decide to go above or below this. You understand? The same thing, if it is rotating like this and I am going below it, then of course it is going to be my counterclockwise case and I will have a very violent instability. But if I go above it, then you can see I will have this second case which is little more benign. So, this is something that you can understand from this experiment. So, we can kind of summarize for this clockwise rotating case that here we see a weak instability at later time as opposed to the counter rotating vortex cases. And for these two cases, the main distinguishing feature is disturbance trail behind the free stream vortex, and the disturbance growth is far lower for this as compared to the other two cases. Okay. Now, this first can be explained in terms of the input adverse pressure gradient, and this is what I told you about the scouring effect. That is exactly the adverse pressure gradient tries to do also. It helps in doing that. In case of clockwise rotation, adverse pressure gradient trails behind the cylinder, while in case of counterclockwise rotation, adverse pressure gradient is created ahead of the cylinder. Those four frames that I showed, you can redo the case, put it side by side, a clockwise vortex and anti-clockwise vortex, and plot those, and you can see what we are talking about. You can also see from a sketch of drawn streamline based on, let us say, inviscid flow model itself, because your captive vortex is very far away outside the shear layer. So, you can draw a sketch, and this is the kind of thing that you are going to see. So, here is a case, that is your wall, this is your convecting vortex, the flow is coming like this. So, if it is rotating in a clockwise manner, what do you see about the pressure gradient? How do you see? You see it from the curvature of the streamline. Where is it maximum? This is here, behind the cylinder. You see, here it goes rapidly. Here also there is a kind of a divergence, streamline divergence, but this is more like straight. Whereas here, even though it was adverse in this part, that is followed by a favorable pressure gradient. So, even if the flow was becoming unstable here, but when it comes very close to the cylinder itself, you actually again impose a favorable pressure gradient. So, that thing is created there, but that is again followed by a rapid streamline. So, this is the case of clockwise case, and you can see in the case of counterclockwise case, of course, this side streamlines are converging. So, you have a favorable pressure gradient, and this side it is continuously diverging, and you see the effect. And you can also now see that in this case, this kind of adverse pressure gradient is over a small region. That is what, if you look at the case 5 plot that I showed, the bulging happened over a very narrow range. It remained very much confined there, not over a large distance in the upstream, because later on again you can see streamlines converge. So, you have a favorable pressure gradient. So, that is what I was telling you about the strategy of avoiding, say, convecting vortices effect, whether you want to go above or below, because the adverse case is a very narrowly focused region, whereas in this case adverse effect is over a large region, and it keeps it all pervading, right. So, this sketch is pretty much revealing that you can understand it. So, again to emphasize the point, you see what happens. The boundary layer stability or instability is dictated upon the impressed pressure gradient from the outside. So, in this case, what is happening? So, your shear layer may be here embedded right next to the wall, but what is the pressure gradient that is imposed? That is given by the streamline curvature, and here you see a very interesting feature. You start off with the adverse pressure gradient, but more or less with a similar divergence, that is followed by a favorable pressure gradient, again followed by a rapid adverse pressure gradient, and again followed by favorable pressure gradient. So, whatever damage that can occur only here. Whereas, in this case, what is happening, this side is decidedly favorable pressure gradient because the streamlines are converging, and on this side flow is decidedly unstable because it is constantly unstable. Okay. So, this is the picture that we draw out of simple streamline consideration. Okay, that is precisely what we are also stating here, that the streamline curvature in each case is the indicator what kind of pressure gradient that you have imposed. For the counterclockwise case, your streamline divergence is ahead of the cylinder, and it is also more pronounced than that is behind the cylinder for clockwise rotating case, right. This is what we emphasized just now. This explains why counterclockwise rotating vortex will create a stronger effect as compared to clockwise rotating. This we actually did a lot of computations and experiments. The experiments are reported in this paper, plus Manojit's thesis, which was a master's thesis done in 2001, and this paper is here in this fast track paper in Journal of Fluid Mechanics. We gave a physical and theoretical explanation for those phenomena. So, we did show that. We will now shortly carry on our discussion on that. Now, in trying to close this discussion on the visual signature, what we note that the displayed evidence is for an instability of a wall bounded shear layer at a streamwise location, where the theoretical investigation reveals absence of unstable TS wave. Later on, I will show you some computed results where the computational domain is restricted to something like where RE delta star at the outflow is less than 500. So, we are talking about a subcritical case, because you know TS wave only begins after 520. So, that is what we are saying, that theoretical investigation reveals absence of unstable TS waves. Now, this is the reason we called it as a subcritical with respect to TS wave. Unfortunately, the initial struggle to establish existence of TS wave was so much that afterwards people do not see anything much beyond TS wave. So, all our vocabulary is with respect to TS wave. So, this is subcritical with respect to TS wave. Okay. There is a very good reason for the receptivity conducted, because why we do a subcritical test is because if we are looking at a supercritical Reynolds number, we talk about the transfer function of the dynamical system that would be very, very receptive to even a trace magnitude of background disturbances. Like what we talked about the case 3, where it was just simply translating towards the end. If there is a rapid time variation, you would see some bit of disturbances growing up, and that is precisely what happens with a supercritical case. So, if you are trying to establish some physical mechanism, it is in your best interest that you do the experiment on a subcritical scenario. Okay. So, that is precisely what is said, that for subcritical state, transfer function is not receptive to small amplitude disturbances, and one needs definitive stronger input to destabilize, really discernible, so that you can reproduce it. You can do this experiment any number of times and you would see the same result. Okay. One has more control in studying the receptivity problem with the carefully designed experiment. Now, we are going to talk a little bit about computations of vortex induced instability. The instability that we see is a precursor to the overall phenomena that we called it as the bypass transition. What we intend establishing here, that if I have a convecting aperiodic vortex that creates a kind of primary instability. And if I have a bulge in the shear layer, then what happens? In the immediate neighborhood of the bulge, I create a secondary instability and I can create a tertiary instability. So, eventually all of this takes over, and we have seen from the experimental evidence for case 1 that it just happens in a very violent manner. Once it appears, it just takes over and spreads over the whole domain, and you see a massive mixing. So, this bypass transition mechanism that we are talking about is a very potent one. So, what we can do is we can think of that we have a Blasius boundary layer, that we can set it up in the lab very easily. People have done it, and then we can destabilize it by a convecting vortex. And these are the references that we have talked about. We did compute the early stages of bypass transition, because we are solving 2D Navier-Stokes equation. Once span-wise mixing start occurring, your results would not be really very relevant. So, that is what we do, is solve 2D Navier-Stokes equation to predict the early stages, to understand the mechanism. Okay. And what you do is take up the Navier-Stokes equation in stream function vorticity formulation, and this you do basically for the accuracy sake, because existence of psi, the stream function would ensure mass conservation in a numerical sense, and basically fluid mechanics is all about vorticity dynamics. So, there is nothing better than working with the vorticity itself. So, this formulation is always recommended. These are all these references that you can see in this, and in this we have defined all this methodologies that is written there. Okay. So, just we mentioned that even for 3-dimensional flow, you can mimic this point of view. That is what Brinkman and Walker did. What they did, they looked at turbulent flow, and suppose the flow is in this direction and I have streamwise vortices. If I have that, then I study a cross flow plane. So, if this is my x direction, if I study in the yz plane, then I am precisely seeing what we are seeing here. So, in a 3D flow, you know, you do not have a stream function, you have a vector potential. But if I am studying in the yz plane, the effect of a vortex in the x direction omega x is exactly like my equivalent 2D flow. So, that is what they have done. So, they looked at the vortex in the x direction and studied the flow in the yz plane. And in this case, what did we see? Kind of an undulation in the streamwise direction when we had omega z in the xy plane, right? Now, if I do this, here also I would see the same thing. I would see what people like to call as peak valley structure. In the spanwise direction, I will have undulating structure. That is exactly the same scenario. So, let us go ahead and try to see what happens when we compute such a flow. As I told you, we are using a vorticity stream function formulation. So, the vorticity dynamics is given by this equation given there for the transform plane representation. We have gone on from the physical to the transform plane to resolve all the phenomena by taking a stretched grid, and if that was the vorticity transport equation, the equation 2 here is the kinematic definition of the vorticity in terms of the stream function. So, this is your Poisson equation, stream function equation, and this h1 and h2 are those scale factors of transformation, scale factors of the transformation. So, if you know how x and y varied as a function of xi and eta a priori, then you can calculate h1 and h2. So, they are functions of xi and eta, but they are still known. This is dictated upon by the grid that you choose. What we did was we calculated the flow in a domain. In the x direction, it went from -1 to 25. Now, what is -1, what is 25? 0 is the leading edge. So, we have taken a domain which is little upstream of the leading edge. So, we want to include the effect of the leading edge, and we have gone significantly downstream, whereas in the y direction we have gone on from this. So, these are non-dimensionalized with respect to the diameter of the cylinder, right. So, this is significantly more than the boundary layer thickness, right. So, if I am talking about a 15 mm cylinder, so this is close to about 30 mm. So, your boundary layer thickness is much lower than this. Okay. And all lengths non-dimensionalized by the core size of the convecting vortex, which is this is the kind of resolution that we took. Today we can do much better, actually. Yogesh does much finer, yes, Shagato does much finer calculation. Take a delta x of the order of this, and in the streamwise direction you do not need to do any bit of stretching. Streamwise direction you do not need to do any bit of stretching, because this is a convecting structure. If you focus your attention at one time, later on that place will have no disturbance, but while the disturbance have moved there. So, it is very impractical to think of a grade which will also move with the convecting structure, and we do not know where the newer structure will come. Even if I decide to track, let us say, the primary instability, I do not know where the secondary and tertiary instabilities will show up. So, the better bet is rather you take a uniform grid spacing, at least in the streamwise direction, and in the wall normal direction, of course, you would like to resolve not only the shear layer, but its instability. So, you take very small spacing very close to the wall. Okay, so, we have used compact scheme, one of the near spectral accurate scheme that we have ourselves developed, given in some of these papers, and those are used to basically study the nonlinear term, because you see most of the instabilities are a kind of a dynamic balance between physical dissipation and the nonlinear convection term. So, the representing the nonlinear convection term is quite challenging. I am not saying the diffusion term is irrelevant. In fact, it is equally relevant, which one can do. Now, in computing these flows, there is only one problem, that is this: we do not know a priori what the strength of that rotating cylinder was. We can get a indirect sort of estimate of it. So, what we have tried to do in these computations, we can treat this strength of the vortex itself as a kind of a parameter and study what it is going to be. You can of course do a parallel study of Magnus-Roffin's effect and work out the strength of gamma. So, that is equally possible. So, basically this is the kind of picture that you see. On the top 3 frames, we have shown the streamline contours, and the bottom 3 frames are vorticity contours. And this blue region kind of tells you about the region where shear layer is there. And you can see there are these faint arrows which shows the streamwise location of the free stream vortex. So, the free stream vortex is much above, but in this frame at t equal to 62 it is here, at t equal to 82 it has come here, and t equal to 90 it has come here. And from this you can see this undulating streamline structure here, right. So, you can see that there is some kind of a vertical eruptions taking place from inside the shear layer. Certain structures pierce through, and this is what we are calling as vortex induced instability. And you can see the similar sort of vertical eruptions in the vorticity contours. Okay. So, I think I will stop here. In the next class we will give out a theoretical model how it creates this instability.